Welcome back to all. So this is the sixth lecture on quantum mechanics, and this time I will give you a brief introduction about the Heisenberg's uncertainty principle. So first of all, let's carry out some thought experiment where we want to determine the position of a subatomic particle like electron by using some probe like electromagnetic radiation. Okay, so if we want to determine the position of this subatomic particle, as we have to use some probe like some X-rays, have to shine this X-rays upon this electron to determine the position of this electron. Now if we want to determine the position of a small object, you should need some probe whose wavelength should be comparable or less than the size of this particle. So why this is so? Let's understood from a very simple model. Suppose we want to determine the size of this particle using this ruler. As you can see that the separation between the two successive lines in this ruler is very much greater than the size of this particle. So by using this ruler, if you determine the size of this particle, we will get the size of this particle with a very high uncertainty. But at the same time, if we use such a ruler whose gap between the successive lines are at least comparable with the size of this particle, then whatever the size of this particle that we will determine will be much more precise than the previous one. So we can understood, to get the very precise value of the size of this particle, we should have a ruler whose gap between the two successive lines should be as small as possible. So similar thing happen here also. If we want to determine the position of this particle very precisely, we should use some electromagnetic probe whose wavelength should be as small as possible. So then we will determine the position of this particle very precisely. So okay, then you are using very small probe having very small wavelength to determine its position, but there is some another associated problem with it. So according to Einstein equation, there is a relationship between the wavelength of that electromagnetic radiation and its energy. This is E is equal to hc by lambda. So smaller the wavelength of that electromagnetic radiation, higher will be its energy. We knew that whenever light is like a electromagnetic radiation or some packets of energy having E is equal to h nu. So if we shine this particle with some electromagnetic radiation having very small wavelength or high energy, this particle will collide with the electron, or this photon will collide with this electron, and if this photon is having higher energy, then it will impart more energy to the electron also. So its momentum will change. So the higher the energy of this probe or lower the wavelength of this probe, higher will be the uncertainty in determining its momentum. So we can see that if we want to see the position of this subatomic particle very precisely using some electromagnetic probe having very low wavelength, then we end up with getting a momentum value whose uncertainty is very high. So similarly, if we want to determine the momentum of this subatomic particle or electron very precisely by using very high wavelength probe, then we will end up with getting its position whose value is very uncertain. So we can see the determination of position of this electron and position of the momentum accurately is not possible simultaneously. So we will denote the uncertainty in determination position of this particle by delta x, and uncertainty determining momentum of the particle, it should be momentum of the particle by delta p. So we can see that from the thought experiment that as the delta x decreases, or we will determine the position of the particle more precisely, then we will end up with delta p, or the momentum uncertainty in determining the momentum of the particle will be high. So this delta x and delta p are related inversely with each other. Now previously de Broglie suggested us an empirical relationship between the lambda or wavelength of the any electromagnetic radiation and its momentum by this equation: lambda is equal to h by p, or we can say lambda into p is equal to h. Now previously, as we have shown that there is a relationship between the wavelength of any electromagnetic probe and uncertainty in position. So from this equation Heisenberg proposed another empirical equation, and the equation is this one: delta x, or the uncertainty in determining the position, into delta p, uncertainty in determining the momentum of a subatomic particle, should always be greater than or is equal to some constant quantity, and that is h cross by 2. And this principle is called Heisenberg uncertainty principle, that has been proposed by scientist Heisenberg in the year of 1920. So we can see from the Heisenberg uncertainty principle that we cannot determine the exact position as well as exact momentum of a subatomic particle. There should be some uncertainty always and this uncertainty is related by this equation, which is known as Heisenberg uncertainty principle. So as we have I have already talked in my early lecture that classical mechanics is a deterministic science where you can determine the exact position, exact momentum, etc. But quantum mechanics is not deterministic, it is probabilistic. In quantum mechanics you cannot tell the exact position of a particle or exact momentum of a particle. You can always say that there is a probability of finding that particle at this position. You cannot pinpoint any particle at that position only. You can say that there is 90% chance that this particle should be in that position. So that is why quantum mechanics is a probabilistic science. So that is why this uncertainty is there. So there is always some associated uncertainty of determining position and momentum of a subatomic particle in case of quantum mechanics. Now this uncertainty principle is almost insignificant for macroscopic objects or larger objects, because the x value or p value are obviously very much bigger than the value of h cross. So there is no significance of this Heisenberg uncertainty principle there. But in case of microscopic object, the product value of this x and delta p is very much significant in case of microscopic object. So as we can see that quantum mechanical science is insignificant when the any subject is higher in size or macroscopic object, but this quantum mechanics become very much important and significant when the size of the object become equal to subatomic particle size like electron, proton or neutron. Now coming back to the very simple Bohr model, this I have already talked about this Bohr model in my previous lecture, where according to the Bohr model the electron is revolving around this nucleus in a certain fixed trajectory, and this trajectory is called orbit, and the distance between the electron and nucleus is also fixed, and the electron is rotating around this trajectory with some fixed velocity. So in Bohr model we can determine the exact position of the electron at a certain time very easily. we can say that the position of the electron at such time, and also as the velocity of the electron is also fixed, we can also determine the momentum of the electron very precisely. So according to the Bohr model, delta x or uncertainty determining the position of the electron is 0, and uncertainty in determining the momentum of the electron is also 0, which is contradictory to the uncertainty principle, because uncertainty principle says you cannot determine the exact position and exact momentum of any subatomic particle very precisely. So this is the first drawback that has been observed, that Bohr model cannot satisfy the Heisenberg uncertainty principle. So to satisfy this Heisenberg's uncertainty principle, we need some better model or better quantum mechanical model. So in my next later lecture, I will show that this formula that has been proposed by Heisenberg empirically can actually be derived mathematically by using quantum mechanics. That I will show you in my other lecture. And in the next lecture, I will talk about the Schrödinger equation, how this Schrödinger equation can be derived empirically and what is the significance. All those things will be discussed in my next lecture. And till then, if you have any doubt regarding this Heisenberg uncertainty principle or any other previous lecture of mine, you can ask it through the comment section, and I will try to answer all of your queries. And do subscribe to my channel named as Chembiasis. This channel is meant for all the chemistry graduate student as well as engineering student. So till then, goodbye and take care. Thank you.